My name is David Din. I am a sales engineer with JuliaHub, and today I'm going to be kicking off our JuliaSim webinar series, in which over the next few weeks, we'll be showcasing the various features and capabilities of our JuliaSim commercial product here. I'll give you a little overview of what the webinar series will entail in just a few slides. But for now, we'll just start off right here with today's webinar, which is going to be the first part of this series. Okay, so today we'll be talking about integrated system modeling in JuliaSim, and we're going to show you how you can bridge the graphical and code-based workflows, all whilst working on a model from a single source of truth. Okay, so I'm going to give you a little introduction to what Julia is, the Julia programming language, as well as the JuliaSim ecosystem, and then we'll get straight into the JuliaSim demo. All right, so not too much fluff today. Okay, so what does the open source Julia programming language aim to solve? So we at JuliaHub have worked with many different companies and programs across various industries, such as automotive, aerospace, AI, and so on. And all of these organizations, regardless of how mature they are, they all face a common problem, a problem we call the two culture problem, or in other words, the two language problem. Okay, so now if you kind of think about the life cycle of various programs and the various phases that programs go through, you might think about the earlier phases of the life cycle when there's research and development being done. Generally speaking, scientists, engineers, and researchers prefer higher level, succinct programming languages that allow them to perform research and analysis without having to worry about things like memory management and low-level programming details and optimization. And naturally, this generally leads engineers to languages such as Python, MATLAB, R, and so on. Right. However, later on in the life cycle, the latter phases of a life cycle, when we move into the deployment phase, software developers, on the other hand, they require performance, reliability, and scalability in their production environments. And this naturally leads them to languages such as C, C++, Java, and so on. Okay, so you can probably already see here, as we transition from early research phases to latter production phases, the models and the frameworks created by the engineers, researchers, and scientists must be rewritten in a language that's suitable for deployment. And ultimately, this leads to refactoring of models, friction in production, and obviously, in many ways, redundant work. So the open source Julia programming language aims to solve this two culture or two language problem by providing a programming language that gives both ease of use and speed to scientists, engineers, and software developers. Right? So modern language design and compiler techniques have made it possible to provide a single environment that's both productive enough for prototyping and efficient enough for deployment of performance-intensive applications. Okay? And of course, all of these statements are supported by both open source and in-house benchmarks. So we just go ahead and take a look at the left side over here. We have data and results from the open source computer language benchmark game program or project. And this is an open source project that is meant to compare how a given subset of algorithms can be implemented in various programming languages. And after they're implemented, we measure how fast and how easy it was to implement those algorithms in these languages. So if you look at Julia here in the lower left-hand corner, you can see that the execution time compared to languages is low. In other words, the execution is fast. And also the compressed code size is also low. In other words, there are few lines of code required to implement these algorithms. On the right side over here, we have some domain-specific benchmarks. Here we have a rigid body system represented as a non-stiff ordinary differential equation. And we can see here that we're going to compare the Julia solution against other solutions implemented in languages such as Fortran, Sundials, the lab, or MATLAB, and the solve. And you can see, as we solve these ordinary differential equations, for any given acceptable error level, we can see that the Julia solution converges anywhere from 1 to 2 orders of magnitude faster than its competitors. Okay, so because Julia is an open source programming language, it's enabled the community to develop modeling and simulation tools for industry use. And sort of at the highlight of this ecosystem is what we call scientific machine learning, or SciML, which is an ecosystem of open source packages implemented in Julia, designed for combining machine learning with traditional numeric methods such as differential equations, optimization, and probabilistic programming. The idea is that we can collect data, whether it's from the real world or from simulation or experiments, and this gives us insight to the real world. Then on the right side, we have models, which bring the power of scientific principles to our analysis. The idea is, as we're combine data and models together, we're able to unlock the best of both worlds: accurate, interpretable, and predictive solutions that learn from experience while staying grounded in reality. And because the SciML ecosystem is implemented in Julia and is open source, SciML fully benefits from the composability, speed, and ease of use that Julia does. So while Julia and SciML are fully open source, we at JuliaHub are building out an ecosystem for enterprises to adopt SciML, Julia, and we are providing a platform to enable this adoption. And JuliaSim is at the center of this ecosystem. JuliaSim is a modeling and simulation tool powered by machine learning. Offers model development, both in the form of visual drag and drop GUIs and IDEs for coding, AI capabilities such as model refinement, discovering physics, calibrating models, optimizing control, and circuitizing models. And we also support various deployment standards, including FMU generation, CI/CD, and so on. And also, we've built out some industry-specific libraries for use with our partners. All right, so JuliaSim is our commercial product, which is built on the open source components from SciML and the Julia programming language. Okay, so what we're planning to do over the next few weeks and starting today is rolling out a JuliaSim webinar series so that we can showcase the various capabilities and features of the JuliaSim application. So we're starting off with this one right here. Today, we'll be showing you how you can bridge graphical and code-based workflows. And just keep an eye out. Over the next few weeks, we'll be rolling some other webinars out, including control design and PID auto-tuning and optimization, embedded controls code generation, generating FMUs from models, and automating discovery of missing physics. And you can go ahead and go to this link right here, and it'll have the schedule of all the upcoming webinars. And we'll send these slides out later, so you'll have these slides, and you'll be able to click on this link as you need. And in case you're wondering how these webinars play into the JuliaSim feature set, we designed the webinar series to showcase the various pillars of the JuliaSim product. So you don't need to attend every single webinar in order to understand what's going on, because each of these webinars will be showcasing a different aspect. But attending all these webinars will give you a holistic understanding of how JuliaSim can be used for analysis from different perspectives. And we'll be using the same model, which is an active suspension model. So we'll be using the same underlying model throughout all of these webinars. So you'll be able to see how we can analyze the model in different ways. Okay, that's it. So let's go ahead and get into today's demo of JuliaSim. So what I'm hoping that you walk away with today is seeing how seamless the workflow is in between our graphical and code-based interfaces. We'll also show you how we can create, simulate, and analyze models in JuliaSim. And we'll show you a little cool technique, which we call model inversion, which is going to allow us to solve directly for quantity, which otherwise would be a little difficult to get a hold of. Okay? So what we're going to do is we're going to start off by building a model from scratch inside of JuliaSim. We'll start with a blank canvas here, and I'll show you how we can build up a mass spring damper so you get a feel of how the GUI works. After that, we'll get into our more complex model analysis, which is the active suspension system. On the right side over here, we can see a visual representation of that system. It's basically just a vehicle that's moving over a road. The idea is we have a road component in our model that's giving off this signal that you see on the left side. The road is mostly flat, except for it has a little bump in the road as the vehicle moves over it. On top of that road, we have a vehicle, which is represented as a seat, a suspension system, and a wheel. And out of this system, we're able to pull out a seat position signal, which we can see on the left side over here. So as you can see, how it works is the seat begins at a position of 1.5, then it moves over the bump in the road, and we see this oscillating effect. Also in the loop over here is a PID controller, which is controlling an actuating force. And force is going to try to damp out the seat response in order to keep the seat as close to the reference value of 1.5 as possible. After we simulate and analyze this model right here, we'll move on to quote unquote inverting our model. And what we'll do is we'll show you how we can create this component and solve directly for the amount of force needed if we want to keep the seat at exactly 1.5. And we'll talk through this problem once we get to it. Okay, so with that, I'm going to go ahead and move to the product, the JuliaHub interface, and we'll get right into it. So here I am on our JuliaHub cloud platform. I'm here on my homepage right now. We see some quick links to various applications, projects I've worked on, various jobs that are running in the background. We also have other pages where we can launch other applications and develop other applications, notebooks, Julia notebooks, like Julia notebooks are analogous to Python Jupyter notebooks. We also have project management, package version management, registry management, and so on. But today, we're going to stay focused on JuliaSim. So what we'll start off with is right here, the JuliaSim graphical user interface. And then in a few moments later on in the second half of the demo, we'll move to JuliaSim Studio, which is the code-based interface. So I'm going to go ahead and click Connect right here to start up JuliaSim. Okay, so here we're greeted with a welcome page. We can choose an existing project or create a new one. So projects are an encapsulation of models inside of JuliaSim. Projects contain all the information needed for both graphical and textual code-based representation of the model in JuliaSim. And projects are stored in JuliaHub as a Git repository, which allows for version control, diffing, and so on. So what I'm going to do is I'm going to open up this project right here, the webinar for this project I just made a few moments ago. This right here, webinar 1, is an empty project. So we'll go ahead and start building off from here. Okay? So before we start doing anything, I'll go ahead and orient you with the interface here, what we're looking at. In the middle here, we have our workspace area. Later on, when we have models open, we'll be able to see the schematics of those models inside our workspace area. Along the bottom here, we have our simulation panel. Later on, when we carry out analysis and simulate our models, we'll see the result of the simulations down here in this panel. And then here, we can see on the left side, we're currently sitting on the library tab, and we have two libraries preloaded into our fresh project. We have the JuliaSim modeling language standard library right here, and we also have the custom library that we created just for today. Okay, so what I want to do is I want to show you how we can create a mass spring damper. So the first thing I'll do right here is I'm going to import some libraries to help me build up that mass spring damper. I'm going to bring in block components, JuliaSim example components, and translational components. Okay, so now I want to expand my library right here, and I'm going to click Add a Component. Once I do that, I can see a new component has been created in my library, and we are now looking at the schematic of this component. And to no one's surprise, the schematic right now is completely blank. What I'm going to do is rename this component by opening up the parameters panel on the right side. There it is. Now I see that my component has been renamed to mass spring damper. So now let's start building this thing up. The first thing I'm going to do is I'm going to give my mass spring damper two flanges or two mechanical ports. And this is going to allow me to connect my mass spring damper onto other components. So you can think of these as connection points. After that, I'm going to add in a mass component. And a spring damper component. We see that this is red. It means it's missing some required parameters. I'll go ahead and click on the mass and expand the parameters on the right side. And where we see an asterisk, those are required parameters. So I'm just going to go ahead and give dummy values for now. So it's just going to place in 1. After I do that, you can see the mass turns black. It's no longer red. And the spring damper, I'm going to give the spring and damping constants right here. Okay. Last thing I need to do here is I need to make sure all these components are connected. And these connections are what enforce physical relationships in between the various components. So here we are. We have our mass spring damper. You can think of the mass spring damper as sort of this box right here. And we're going to be able to, you're able to use this component to build up more complex component in a component-based approach. And this right here, these flanges right here, this is how you would connect this mass spring damper onto other models or other components. Okay, so now that we have a feel of how to do something from scratch, let's go ahead and move to the active suspension model we previously mentioned. So what I'm going to do is I'm going to expand the JuliaSim example components library. There I'll find my active suspension model. What I'm going to do is I'm going to make a copy of this model so we can do analysis on it. So I right click on it, select duplicate. And here I'm going to send it to my destination library. So now we see inside my library right here, I have an active suspension model. What I'll go ahead and do is I'll expand the parameters on the right side, and I'm going to rename this model to something else just so I don't confuse it with the standard model, the standard unmodified model out of the library. Okay, so here it is, our active suspension model. Again, what we're looking at here is a vehicle that's moving over a road, right? We have road and road data, which is giving off a road signal. We have a vehicle represented by seat, suspension, and a wheel moving over that road. We're able to pull out a seat signal right here. Based on that seat signal and the desired reference value, a specific error value will come out of this block right there. And based on that error and the gains inside this PID controller, a certain amount of force will be applied onto the seat in an attempt to dampen the response. So before we run this analysis, let's go ahead and see what the seat response looks like as we move over the road without this PID controller in play. So what I'm going to want to do is I'm just going to go into this PID controller and set all the gains to 0, effectively removing it from our loop here. So I'll click on PID and expand the parameters on the right side. So here we can see that KP, KI, and KD have already been given default values right here. KP, KI, and KD. We already have default values living here. So if we're wondering, hey, where are these default values coming from? Turns out this PID block is able to inherit values from its parent level component. So what I'm going to do is I'm just going to click somewhere over here in this blank canvas. I'm just click over here. And by doing that, I change my parameters panel back to my active suspension. And if I scroll down to the bottom over here, I can find those default values we were just talking about. So here, KP is 1, KI is decimal 2, and KD is 20. And these are the default values being inherited by the PID block. So if I want to set all these values equal to 0, I can choose to do it here at the parent level component. But instead, what I'm going to do, I don't want to lose these values. So what I'm going to do is instead, I'm just going to go back to my PID block. And here, instead of using the default values, I will specify my own values within the PID block right here. And the value I'm going to specify for each of these gains is, of course, 0. Okay, there it is. So now we have this set up properly. Let's go ahead and run an analysis and see how the seat response looks like. So on the upper left-hand corner over here, I'm going to select the Analysis tab, and I'm going to go ahead and add an analysis under my active suspension. Here, we're going to add a transient analysis type because we're interested in the seat response over time as we move over the road. Okay, I'm going to go ahead and click Run right here. So here, we see our simulation panel is now populated with 3 tabs: Definition, Code, and Results. We have a definition for this transient analysis. The target model is, of course, my active suspension. And we also have arguments for this analysis, the relative tolerance, absolute tolerance, start and stop time. And also, we have this code tab. So this right here is the code-based representation of this analysis. Okay, so remember, everything inside of our projects and our models have code-based representations that allow these objects to be represented both in the GUI and also our code-based interface, which we'll get to later. So for now, just keep this in the back of your mind. But the results have finished being collected and simulated. So I'm going to go ahead and create some plots with some signals. Okay. So what I'm going to do right here is I'm going to go ahead and plot the seat signal right here, and also the amount of force that was applied to the seat. And of course, this value right here, the force, I expect this to be 0. I'm going to create a visualization. I'm going to add the seat position right here. And then I'll also add the force just to confirm that the PID controller is not in the loop. Okay, so here we can see the force throughout the 10-second simulation remains at 0. So that's good. That confirms that. And then on the left side right here, we have the seat signal. We see that the seat begins at a position of 1.5. And as it moves over the road, it oscillates down to as low as at about a position of 1.00, all the way up to a position of about 1.99. And if we want to plot the road signal on this, oops, hit the wrong button. If we want to plot the road signal on this plot, we can also do that. So we have an understanding of the exact moment that the vehicle moves over the road. Okay, so now we have an understanding of the seat response without the PID controller. Let's bring back the PID controller, okay? So now I'm going to go back into my PID block. And now instead of specifying values of 0, I'm going to go ahead and use the default values for all these fields. Once that's done, I can go ahead and hit Run to re-simulate our model. Okay, let's go ahead and plot the seat position again, and also the force. Okay, so the first thing we can see is the force is now non-zero. There's being a force applied on the seat throughout the simulation of up to about 25 newtons and as low as negative 27 newtons. And we can also see that the seat position, once again, it does start at a position of 1.5, but now it oscillates only down to about 1.05 and as high as at about 1.9. So there's a little bit of damping going on, not a ton, but there definitely is a little bit of damping, seeing how our seat response is different, and now we can also see the force being applied on the seat. Okay, so now let's ask a different question. Let's say we are the hardware team, we're the mechanical engineering team, and we're looking at this system and we're looking at, hey, this actuating force, we want to know what the requirements are for this component right here. We need to know that if in the ideal case scenario in which the seat position is able to perfectly track 1.5, in that scenario, what is my force requirement? Okay, so there's two different approaches to this. The most common approach that someone might take for something like this is the first thing you would go into is this PID controller. You would go into this PID controller and you'd run auto tuning or optimization on the PID controller in order to find the optimal gain values such that the seat is able to track 1.5. And based on whatever gain values that PID is set to, we'll have an output force that we're able to measure. So that is one approach to doing this, but that of course requires the controls team to do their work before the mechanical engineers can even get their answer to what the force or mechanical requirements are, right? So what we're going to do here is we're going to invert this model and solve for the force directly. So what does that mean? We're going to create a new component and we're going to place it right here. What this component is going to do, it's going to take in the seat signal and it's going to take in the desired seat position. Based on that, it's going to tell us exactly how much force is needed such that the seat stays at exactly 1.5. And we're going to do this without having to auto-tune or optimize this PID controller at all. Okay, so we're going to be able to solve for this directly. So I'm going to go ahead and create this component that I mentioned, this component right here. We're going to call this reverse causality. And we're going to move over to the IDE, the JuliaSim IDE, in order to create this component. So what I'm going to do is I'm going to go back to my library tab here, and I'm going to click this button right here in order to save, in other words, commit my project to JuliaHub. I see that little check mark right there. It means everything's good to go. Now I'm going to select this JuliaHub button in the upper right-hand corner. Okay, so now you see we're back into the JuliaHub interface, but instead of being on the home page, now we're sitting on the projects page. And we can see that this project, we're on the webinar 1 4th March project page, which is the project we are currently working on. And here, once again, these are all the files needed for both textual and graphical representation of the model in JuliaSim. This is what you're looking at right here. So I'm going to go ahead and hit the connect button right here to connect to JuliaSim Studio. In other words, the code base interface for JuliaSim. Okay, so what we get with this interface is a full-featured programming language. Pardon me, let me go ahead and activate this environment real quick. Activate this environment and instantiate everything. Okay, great. So what we get with this interface is a full-feature programming language in Julia, which is going to allow us to examine, modify, and analyze different aspects of the model. So you can sort of imagine in the lifespan of a program, you might have different types of users who need to work on this model from the same source of truth. You might have mechanical engineers or control engineers who maybe prefer a graphical interface like this, where they can easily drag and drop various components and connect them together to build up models. On the other hand, you might have users such as GNC engineers or other users who prefer code-based interfaces like this, where it's more easy to keep track of equations and perform other types of low-level analysis on these models. Right? And the beauty here is that both teams can work off the same source of truth. This is the source of truth right here. We can work on the same source of the truth, both from the graphical user interface and the code-based interfaces, okay? And that's what the JuliaHub project is all about, right? Being that get back single source of truth. Okay, so what I'm going to do now is I'm going to go ahead and go into my JuliaSim modeling language folder on the left side right here, and I'm going to create a new component. And what I'm going to create is a reverse causality component. Reverse causality.jsml. I spelled that wrong. Great. Okay, so let me see here. What are we looking at right here? What we're looking at is I just created this file right here, and I just copied and pasted the code you see. So I'm just going to explain what we're looking at. So what we're doing is we're creating a component named reverse causality. This component is going to inherit from or extend another component from the block components library. And the component that we're extending or inheriting is the 2 input, 1 output component. The 2 input, 1 output component. Within the 2 input, 1 output component, so within SI2, S0, the 2 inputs are labeled as U1 and U2. So the relationship that I want my reverse causality component to enforce is U1 is equivalent to U2. In other words, I need my reverse causality block to enforce that its 2 inputs are equivalent to one another. Okay, so just go ahead and keep that in the back of your mind right now. So I'm going to go ahead and do using. Okay, so while this is going, I want to point out some other things. Right here, we have this my active suspension object in the JSML folder, and we can see here that this my active suspension has some components that we might recognize, right? A wheel, car and suspension, seat, road data, and so on. And if we start to scroll down this, we might see other things that are sort of familiar to us. Like, for example, we have these parameters down here, KP, KI, and KD, right? So where did these come from? If we go back, where have we seen this before? So if I go back to my interface over here, my GUI, and we see the my active suspension schematic right here, we actually have a code button right here. And if you look at the code-based representation, this is exactly the same thing we're seeing over in the IDE, right? We're seeing everything here. We see the wheel, car suspension, seat, and at the bottom, we see those same parameters, right? So this right here kind of reinforces the idea that we're looking at the same thing, the same code-based representations. Okay, so now I'm going to go ahead and to solve this. Let's go ahead and solve our model from the code-based interface right here. Okay, so now we have right here a plot of the force simulated throughout our model. And if this plot looks a little familiar, that's not a surprise, because if we go right back over here inside of our GUI, the last plot we created was this force plot. And to no surprise, these are the same plots because we are operating off the same single source of truth. Okay? And we know the force isn't different yet because we have not incorporated our reverse causality block into the model. Just right now, we're just simulating the same model. And the last thing I want to show you is using LaTeXify. Okay, so what we're looking at right here on the right side are the dynamics of the model. So the dynamics of the model are represented right here. And what's interesting about this is that the compiler generated these equations for us, right? In a tool that follows a strictly causal framework, you as the user are responsible for deriving how one variable affects another. In a tool that allows for acausal and component-based modeling, such as JuliaSim, we're able to define relationships within components without specifying the direction of influence, and the system is able to generate the causalized version of the model for us. All right, this is very powerful. Okay, so now that I'm done right here, what I'm going to go ahead and do is I'm going to go ahead and commit my changes, add new component. Okay, now I'm going to go back to this interface and refresh now that my changes are committed. Okay, so now over here, I can see my reverse causality component that we just created, right? We just created this now. Now it's populating inside of our library. I'll go ahead and open up this y-axis suspension right here. And so I'll drag reverse causality onto my block right here, or my diagram. And I'm going to zoom in just a second and look at this reverse causality block, right? So it looks like we have two inputs and then one output. If I hover over this, it looks like one input is labeled as U1 and another input is labeled as U2. So where have we seen this before? So well, if I go back into the IDE, remember, we created this relation when we created the reverse causality block. And U1 and U2, as mentioned before, are simply the inputs to this block. So what I'm going to do right now is I'm going to hook up the inputs to the seat signal and the reference signal. Then I'm going to sever this connection between the PID controller and the force because the PID controller is no longer driving the force. Instead, our reverse causality component is now driving this block. Okay, so again, what's going on here is this reverse causality block is going to enforce the relation that both its inputs are equivalent to one another. And it's going to do that by outputting the correct force value. So I'm going to go ahead and move to analysis, and I'm going to run this analysis. So first thing we want to do is let's go ahead and look at the seat position to make sure it does remain at 1.5. And indeed it does. The seat position is 1.5 throughout our entire simulation. And now we can add the force signal. And there it is. So this, what you see on the right side here, is the force signal required to keep the seat position at a perfect 1.5, right? And we were able to figure out this force value without doing any kind of optimization work around this PID controller, right? We're leaving that work for another team. That's not what we're interested in. We're doing system hardware requirements, and we need to know the force requirements here. And this gives us insight to that, right? We can, if we want, we can zoom in on this plot just a little bit right here. And we can see that not only does actuator need to be able to output 240 newtons of force, it needs to be able to go from about 0 newtons of force at half a second all the way to 240, about less than 1 second later, right? So it gives us insight into our system requirements. Okay, so that's it. That's it for this part. What we did right there was we answered the question of what force we need without having to work on the PID controller at all by using this reverse causality block. And the beauty is we didn't have to rearrange any equations, right? We didn't have to rearrange what inputs, which things are inputs, which are outputs, or any of that, right? All we had to do was create this block and we changed some of the connections and we were able to answer that question. Okay, so what did we just do right now? What we did was we started off with a blank canvas and we showed you how you could build a mass spring damper from scratch. After that, we moved on to our active suspension system and we simulated it to observe the seat response as it moved over the bumpy road, both with the PID controller in play and without it. Then we moved to the IDE to create this reverse causality component, and that component allowed us to determine the exact amount of force needed to keep our seat at a perfect 1.5 without having to do any kind of optimization analysis in between. And that's it. So what we went over today is we gave a brief overview of what the Julia open source programming language is, as well as SciML. And then we covered JuliaSim pillars of capabilities and features and its ecosystem. Today, we kicked off the webinar with showing how you could bridge your graphical and code-based workflows. I recommend everyone check out this link when you get a chance. And there you'll see signups as we begin to populate that page. There will be signups for these other webinars right down here. Again, my name is David Din. I'm a sales engineer with JuliaHub. If you need me for any kind of questions, go ahead and email the company or you can email me directly. And that concludes my presentation for today. Thanks for joining us. And I will hang around for a few more minutes in case there's any questions. But if you need to go, have a great day. And you'll hear from us in the form of a follow-up email along with some links for and some slides. All right, so thanks a lot, everyone.
In case you have any questions, you can type it in the Q&A section and we'll answer them in the order we receive.
Thanks, Dean. Have a good day.
There's a question from Chris.
Can you run it at 20 seconds to see what happens? Oh, let's see. So I will go ahead and let's go ahead and redo this, reconnect this. So it does. Yes, it indeed does continue to diverge. Making me keep me on my toes, Chris, having me do stuff out of script. But yeah, I'm glad I was able to answer that question. Hopefully that gives you a little more insight. So, of course, what this tells us is the PID controller is not optimal yet. Because of course this is the game values here are just dummy values. They're not optimized. But yeah, good question.
Yeah. There's another question from Chris.
If I have a data set of a physical system recorded as a time series, can I create a model from this time series? So I actually don't know how to answer that question right now, Chris, but I am going to write that down and we will follow up either directly with you or in the follow-up email. But thanks for the question. Yeah. No, Chris, we actually did change the PID controller values back to the default values at some point. So the PID controller is in play, and we also kind of know it's in play because there's an actuating force right here. The PID control gains were set to 0. This would be here. I'll go ahead and do it. Let's go ahead and do it. Now I'll set it to 0. Run the simulation again. So this is the response that with the PID gain set to 0. The previous one, the gains were the default values, but it didn't have a huge damping effect, even though it was there. So Chris, okay, so the reason why it doesn't damp to 0 is because when we simulate it for more than 10 seconds, there's actually 2 bumps in the road now. That's why it doesn't damp to 0. And then can the results be exported to CSV file? The answer is yes. But that is, yeah. So the answer is yes. And that is a feature that it's going to be built in before the version 1 release of this. So yes. I cannot run for, can I? So I'm gonna, let's see. Let's see what happens here. You're making me nervous, Chris. Let's see if this does it. No worries. We need to be able to answer these questions. Okay, let's see. Let's see the C position right here. Yeah, that looks, hopefully that's satisfactory for you. Let's see. Oops. Yeah, look better? No problem. Jose, how easy would it to analyze the frequency components of the seat position? Yeah, so we do have tools to do that analysis. That is definitely beyond the scope of today and also what I'm prepared to speak about. Um, but that, if you ask that question in one of these webinars, the engineers who are presenting those will be a lot more equipped to answer that type of question. But I will also, let's see, Jose, I'm going to go ahead and write down your question, and we will also follow up with you to give you something more specific. Okay, if there's no more questions, we'll go ahead and end the webinar right around there. Thanks a lot, Jose, Chris, and Jan for the questions, especially Chris. Love the questions, and I'm glad I was able to answer them. So you'll hear from us in a follow-up email, and if you have any other questions, go ahead and reach out to us. Thanks a lot. I think we can end it right there, Sanjeev.
Yep. Thank you, everyone. Have a great day.